Today, we're diving into one of the most exciting frontiers in all of AI. We're not just talking about teaching a machine to do one thing really well. We're talking about teaching it how to learn anything. So let's start with a little puzzle, one that really gets to the heart of a massive challenge in artificial intelligence. You, a human, can walk up to a brand new, complicated coffee machine and probably figure it out in a few minutes. But a standard AI? It might need literally millions of attempts to do the same thing. So what gives? Why the huge gap? Well, it really boils down to one word: experience. See, when you're tackling that coffee machine, you're not starting from zero. You're pulling from a lifetime of pushing buttons, reading instructions, and just, well, interacting with the world. Most AI systems today don't get to do that. For every single new task, they start over from a completely blank slate. So you can see the big goal here, right? Researchers want to close this gap. They want to build AI that can take what it's learned before and apply it to new situations, fast, just like we do. And this brings us into the really fascinating world of meta-learning. At its heart, meta-learning is a really powerful idea, and it's simpler than it sounds. The idea is you don't train an AI to become an expert at just one thing. No, you train it to become an expert at the process of learning itself. The end game here is an AI that can solve a brand new problem it's never seen before with just a tiny bit of experience. And you see this idea of few-shot learning all over the place. For example, imagine you train a model on thousands of different little image sorting tasks. Then you can show it just 3 pictures of let's call it a WUG, and 3 pictures of a DAX. And then bam, you show it a new picture and it can tell you which one it is. For a standard model, that would be totally impossible without tons more data. You know, this is actually the magic behind what we call in-context learning in the big language models we all use. When you give it a few examples in the prompt, like, hey, correct this grammar, the model isn't actually retraining. It's using its meta-learning ability to figure out the pattern you're showing it and apply it instantly to something new. Pretty cool, right? Okay, so that's the idea. But how do we actually apply this to something like a robot learning a physical task? Well, one of the most successful ways to do this is something called the black box method, which basically treats the AI like a sequence model that has a very, very special kind of memory. The key here isn't just that it remembers its recent attempts. It's what it chooses to remember. It's not just about what it saw or even what it did. There's one more crucial piece to this puzzle. And here's the secret ingredient. It remembers the rewards. So the AI's policy, the thing that decides what to do next, isn't just looking at the past states and actions, it's also looking at the rewards it got for those actions. That feedback is what tells the agent, hey, that thing you just did, that was good, or that was bad, for this specific new task. This is what lets it adapt on the fly. So here's how the training actually goes down. Think of it like a super intense boot camp. The agent gets thrown into thousands of different tasks, say thousands of unique mazes. In each one, it gets a couple of tries, what we call episodes. Its entire experience, the good, the bad, the ugly, it's all stored and used to update its core strategy. The AI isn't learning to solve one maze, it's learning the general skill of explore a new place, then use what you learn to get to the goal. All right, so after all that grueling training, what's the payoff? Let's take a look at what happens when we give our meta-learned agent a brand new maze, one it has never, ever seen before. So, in its very first attempt, the agent kind of wanders around. It behaves like a scout. It bumps into walls, it takes wrong turns, and you might look at that and think it's failing, but it's not. It's actively exploring and building a mental map of this new place. But then, you watch the very next episode, and it's like a different agent. Everything changes. Using the memory of that first clumsy attempt, all those states, actions, and rewards, it now makes a beeline straight to the goal. No wrong turns. It has learned and adapted in a single shot. And this chart just shows you how dramatic that change really is. The time to find the goal absolutely plummets after just that one single trial. We're not talking about a small improvement here. This is a fundamental shift from exploring to exploiting, all because it learned how to learn. Okay, this all seems amazing, right? Almost like magic. But, of course, there's a catch. And it's a deep, really difficult challenge that hides under the surface of all this success. It's a tricky chicken and egg problem. And this quote really sums up the whole paradox. In reinforcement learning, an agent learns from getting rewards. But in a lot of complex tasks, you only get a reward after you've already done a bunch of things in the right order. So how are you supposed to learn the right sequence if you never get any positive feedback until you've already somehow stumbled onto the solution? Let's make this real. Imagine a robot in a building. At the entrance, there's a sign that says, "The goal is in the third hallway." Now, if the robot just gets lucky and randomly wanders into hallway 3, sure, it gets a reward, but it doesn't learn the strategy of reading signs. If it explores poorly, checking hallway 1, then 2, then 3, it learns a really slow, inefficient strategy. But here's the worst part. If it does the smart thing first and reads the sign, but then messes up and doesn't find the goal, it gets 0 reward. It learns absolutely nothing from its smart first move. So you see the problem, right? For the agent to learn the right strategy, it has to get lucky twice, in the same run. It has to perform a good exploration action, like reading the sign, and a good exploitation action, like following the instructions to the goal. The odds of that happening by random chance are often astronomically small, which makes this whole process incredibly hard to train. So how do researchers get around this? Well, if just optimizing for that final reward is too hard, then the path forward is to kind of change the rules of the game, to break the problem apart. Instead of only giving the agent a cookie for solving the entire puzzle, researchers are now adding extra goals. One really cool approach is called posterior sampling, which basically encourages the AI to be curious. It learns to form little hypotheses about the world, like, I bet the goal is in hallway 1. And then it gets rewarded for taking actions that test that hypothesis. It turns exploration from a random walk into a deliberate search for information. Look, solving this exploration problem isn't just about getting robots to solve mazes faster. This is a huge step toward building AI that is truly general and adaptable. The kind of AI that could learn to use a new piece of software just by reading the manual. Or maybe, just maybe, finally figure out that new office coffee machine on its first try. The question is no longer just what an AI can learn, but how fast and how well it can learn to learn, well, just about anything.